Hello! Hopefully you've had a chance to work through the uncertainty principle between the position squared operator and the momentum operator and derived the corresponding uncertainty principle. In this video, we're going to go through some of those details to see what we get. So in order to calculate the uncertainty principle between the position squared operator and the momentum operator, we need to calculate the commutator between the position squared operator and the momentum operator. And whenever we're talking about operators, in order to figure out what to do with the operators, we always have to act on them times a wave function. So we're going to act on these operators, the commutator of these operators, on a wave function psi. So let me just write out the commutator. So writing out the commutator, it is the position operator times the momentum operator acting on the wave function minus the momentum operator times the position operator acting on the wave function. Now the first term, I have the partial derivative acting directly on the wave function. But the second term, I actually have my partial derivative that's going to hit, alternatively, the position operator squared, which when it operates on the wave function just becomes x squared. And it's also going to operate on the wave function itself through the product rule. And so I'm going to have two terms from this operator action here. And so if I have the partial derivative first act on x squared, then I'll get this middle term here. And then I'll also have a term where the partial derivative skips the x squared and acts directly on the wave function. And so then I'll have this last term on the second line here. So I can actually do the derivative of the second term, do the derivative with respect to x of x squared. The other terms are actually going to cancel each other out. You can see that the first term and the last term actually cancel each other out. They're exactly the same. They just have a minus sign. And so I get the middle term after I take my derivative. So after I take my derivative, I get a power of 2. There's an x still floating around. I pulled the I upstairs rather than leave it downstairs. And then that's all acting on psi. So in order to figure out what the commutator between x squared and p hat are then I just have to strip off the psi now. And so to make this true for all wave functions, I say that the commutator between x squared operator and p hat operator is now 2i h bar x hat. So I just stripped off the wave function there. Well, so that's good. Now I can use this in my generalized uncertainty principle between the position operator squared and the momentum operator. So I just insert it on the right-hand side of the generalized uncertainty principle. And I have to take an expectation value as well. So when I take my expectation value and then I also square everything, there's some 2's that cancel, there's some i's that cancel, and I actually get this really nice, simple result that the right-hand side is just h bar squared times the expectation value of x squared. Or I can take the square root on both sides to find that the uncertainty in the position squared times the uncertainty in the momentum must be greater than or equal to h bar times the absolute value of the expectation value of the position. And again, I'm just kind of jokingly calling this the Underwood uncertainty principle. Of course, you can call it whatever you want. So this doesn't have a name. You can make your own uncertainty principles by picking any two operators, A and B, and calculating their new uncertainty principle there. So can then we have a simultaneous definite states of both position squared and momentum? Is that possible, at least in principle, from what we have here? Well, it looks like it would be possible in principle if the expectation value of x vanished. So if the expectation value of x vanished, then the right-hand side of the uncertainty principle is 0. And so then in principle, it's possible to have 0 times 0 equals 0. So you could have a definite state of both position squared and momentum and still satisfy this uncertainty principle. Again, contrast that with the usual Heisenberg Uncertainty Principle, which says you can't have a non-zero product, or you can't have, a zero product between the uncertainty in position and uncertainty in momentum. You always have to have something that's non-zero. Here, it seems like you could, in principle, make something that was that has that product equal to 0. In practice, it's very difficult to have to imagine a state that will have 0 uncertainty in both position squared and momentum, but you could, in principle, have one that has have a state that has zero, say, uncertainty in position squared, or zero uncertainty in momentum, and then just something finite for the other variable. And so then the product is still equal to 0. Okay, so this was an example of how to derive your own generalized uncertainty principle from the general formula.